Welcome to massive open online course on basic principles and calculations in chemical engineering. So, in this module of energy and its forms, we will discuss about the principles of energy. In the previous module, in lecture 16, we have discussed about the process with phase change, and also based on that principles of the phase change, we have discussed about the different laws of that equilibriums when there is a change of phase, especially for condensation and vaporization process. There also we have described how to do that material balance with those that principles, laws of that condensation and vaporization, and those are actually based on the vapor pressure concept at equilibrium conditions, and also the partial pressure which is depending on that vapor pressure, as well as that mole fractions of the components in the liquid phase which are in equilibrium with the vapor phase. And also we have described that different phenomena of that process variables for this equilibrium condition during the phase change, like humidity, dew point, even bubble point temperature, relative humidity, saturation, humid volume, enthalpy, absolute humidity, how to calculate, all those things we have described there. In this lecture, we will discuss the concept and units of that energy system, and how to do that energy balance, and what are the basic equations for that energy balance. So, in this module we will start this energy balance. In this is lecture especially for the that how that energy is being defined, and also what are the units and how that energy balance can be done in open system and closed system. And based on this energy conservation law, we will be doing that energy balance for the process systems in the successive lectures of this module. And so we can first talk about that concept of that energy. What is that energy that we have to know first, how it can be defined. Basically this energy is represented by the phenomena of that ability of work, or you can say that what is the strength of you or particular system, or in a process equipment, or you can say that whenever there will be a execution of any plant, what should be the overall strength or power, you can say that ability of that overall plant to give you certain yield. So, in that case we can say that energy can be defined as the term strength or ability to work, which is basically derived from the utilization of physical and chemical resources, and this is especially to provide light and heat, or to work machines there. And in overall based on this that heat or work of the machines will be regarded to assess that whole process plant energy systems. And also we can say that this energy is basically a quantitative property that must be transferred to an object in order to perform work on. So, in physics generally this energy is actually considered as a quantitative property, and this quantitative property must be transferred to an object in order to perform some work on the system. In this case, you will see that whenever you are going to assess some process system based on the quantity of energy, you have to express this energy by a certain symbol. Generally, the symbol for energy is represented by E, and of course, you have to express this quantity by a certain unit, that is basically in SI system is joule. So, the common symbol for the energy is used by the letter that E, and in standard unit is generally considered as as joule there. And you will see that whenever we are talking about that energy, you cannot actually destroy or create that energy which are universally available there. Only thing is that this energy whatever available, that you can convert this from one form to another form, and this energy can also be transferred from one point to another or from one body to another body. Like any heat object is being touched with a cold object, what will happen? You will see that heat energy will be transferred from this hot body to the cold body. So, this heat energy is transferring from one body to another body, and it can be also transferred from point to point, like in a same object or in a same material. If there is a temperature difference between 2 points, you will see that the temperature will be moving from higher temperature to the lower temperature. So, in that way you can say that the heat energy will be transferred from one point to another point. And also this energy transfer, you can say it will occur by flow of heat or by transport of mass or by performance of work. Like suppose if any heat is supplied to any object, you will see that that object or material will be heated with respect to time, and it will be changing its temperature from higher temperature to the lower temperature, or cold body may be transferring from lower temperature to the higher temperature. So, in that case the flow of heat is the main carrier for the transferring of energy, and in that case sometimes you will see in the convective mode, if suppose fluid element, if it is heated and if it is flowing with a certain velocity or at a certain flow rate, you will see that the mass of this fluid will be carrying that heat energy from one location to another location, and this transfer of this heat by this mass flow rate will be that enhanced by just changing its flow rate, or you can transfer that heat energy at a certain rate based on the fluid properties. And also you can transfer this energy by performance of work also. If suppose any pump is that transferring any liquid from one position to another position, you will see that there will be a certain heat energy will be generated because of that friction of that fluid through the surface of the that is conduit through which that fluid will be moving. So, because of that viscous effect or friction of that fluid element over this solid surface, you will see there will be some frictional energy. That frictional energy will be converted into heat energy. So, in this case you can say that how much work is done by that pump to transferring this fluid from one position to another position, they are according to that the heat energy will be produced. Another system, like that if suppose in a closed system, if you that increase the movement of the molecules just by doing some work on the system, you will see that the closed system will be heated up because of that internal friction of that fluid element or that gaseous element in the closed vessel, just by raising its temperature. And also you can say that this change of this energy by raising this temperature, because of that work done on the system, you will see there will be increase in energy, and that increasing in energy will be called as internal energy increased. So, in that case you can say that you can increase the heat energy or internal energy, or you can say that if you are working on a particular system like piston at a certain pressure, and if you decrease the volume or increase the volume just by increasing the pressure and lowering the pressure respectively, you will see that the systems will be generating some energy. That energy change will be considered as that internal energy. So, in this way the heat may be that produced or generated or by transferred by the performance of the work. Before going to that performance analysis of the system, you have to know that why we should know that about energy which will be required for that particular system. Now, we have to know certain energy systems, how much energy is being consumed, how much energy is supplied there in a particular system. So, before going to analyze that, you have to design that system, and after designing that system you will see that this mass of energy will be released or consumed. But that design of course will be related to that energy consumption and that the energy utilization there. So, how much energy will be required for that operation of particular systems, based on which that design system will be designed or unit will be designed. So, for that the knowledge of that energy to be required for the design of a process unit, like it will be helpful to design the pump motor. That if you suppose supply some electrical energy and this motor will be rotating, and based on which you will see that some energy will be produced, and based on which that energy will be transferring to another form to do some work that will be some useful to produce some that valuable products. So, in that case the designing of that pump motor or some other process unit, that will be requiring how much energy to be required or power to be required, that is basically specially for that pump to pump certain amount of liquid from a storage vessel to a process unit. Also, how much energy is required to convert certain amount of liquid at a particular temperature to that steam at another temperature. So, it is also required, and also that hydrocarbon mixture is distilled to produce a liquid and vapor useful products. In that case some energy is required to distill that hydrocarbon mixture. because anyway you have to heat up that hydrocarbon mixture, and based on the boiling point of that hydrocarbon mixture components, you know that lower boiling point liquid will be vaporized easily, and it will be coming up to that column, and it will be separated from that liquid phase, and then it will be collected as a liquid after condensation. And for boiling up you need some boiler, and there also that heat is required. So, for this boiler you need heat energy, and also condensation you need also that some external work to be done there. So, for this operation of distillation to get this useful product of liquid and vapor, their energy will be required, and this energy input to that distillation column, based on which it will be assessed how much it is required for a certain amount of steam that is to be supplied to the process, a certain amount of hydrocarbon mixture. Also you will see that some other aspects also this heat energy or some energy is required there. Suppose a highly exothermic chemical reaction that is takes place in a continuous reactor. Now, if there is a certain percentage of conversion is to be achieved by that reaction, now you have to supply some energy. Now, you have to know what rate of energy to be supplied from the reactor, so that you can keep that reactor at a constant temperature, because whatever energy will be released by that reaction, you have to remove that energy. Now, to removing that energy you have to know you have to use some that process unit like heat exchanger, or you can say that some other cooling device by which you can that remove that heat energy which is produced by the reaction. Now, in that case you have to know what will be the amount of heat to be that required to be removed to keep the contents in the reactor at a constant temperature. Another important aspects where the energy is required to know that how much coal must be burned each day to produce enough energy to generate the steam. We know that whatever energy we are getting, maximum energy is coming from burning of coal by producing different valuable gaseous mixture, and from which we are separating, and then we are getting different type of useful products in daily life. Now, also you will see that whatever electricity we are using, that is actually being produced based on burning of coal. Now, in this case how much coal will be burned to produce this type of this mass of energy. So, for that you need to know that how much energy to be required for its kind enough to generate the steam to run the turbines to produce enough electricity to meet the daily power requirements of a particular city or some other that other requirement. So, in that case you will see that whenever coal is burned, that coal will give you a certain amount of gaseous mixture, and that gaseous mixture you will see that will give you or will be used to that for rotating that turbine, or that gaseous mixture can be used to synthesize some hydrocarbon mixture that will be useful for our daily life. And also coal is also used to that generate the steam from the water. So, that heat energy is produced by simply burning of coal. So, burning of coal will give you the heat energy, and that heat energy will convert that liquid water to its steam, and then steam to be supplied to the turbine, and whenever turbine will be rotating, that rotating turbine will generate that electricity. So, in this way how much electrical energy will be produced by burning this coal, and whenever coal will be burned, how much energy will be produced, and also what will be the amount of coal will be supplied, based on which what will be the energy will be produced, that should be known for that operation. Another important aspects of that chemical processes which are being executed, and also those are required for their operation several units, and like a number of reactors, a number of compressors, distillation column, mixing tanks, evaporators, filter presses, and other materials, that handling and separation process unit. Each of the unit either requires or releases some energy. So, that amount of energy to be calculated, and also that should be controlled based on that amount which are being coming as per calculation, as per requirement. Also, how can the process operation can be designed to minimize the total energy requirement. So, that also can be assessed based on the energy balance, and also how much energy to be required for that. And also overall process plant analysis, whether it will be economic or not, that is actually assessed based on that energy requirement for the whole plant for producing certain useful products there. So, that is why we need to know that energy and its also importance of that balance there. Now, before going to that energy balance equation, again you have to know what are the different types of energies also there, and what are the sources of that energy. You know that there are two types of energy, one is called renewable energy, another is called non-renewable energy. Now, renewable energy, it is called, what is that, the solar, wind, water, hydro, geothermal, biomass, wood, tidal. This type of energy, it is called renewable energy. In this case, many of the earth's energy resources are available on a perpetual basis. So, these include this solar, wind, water, geothermal, biomass, and these energy are called renewable energy. And some energy sources can be replaced over relatively short periods of time, and this includes wood and other biomass, all are considered as a renewable energy. Whereas, you will see that in our modern industrial society, which are dependent upon the energy, and those energy comes from that just by come from that natural resources like fossil fuels, coal, petroleum, oil and gas, like this. In that case, fossil fuels are the major sources of energy in developed and industrialized, you can say that, nations. Solar energy from the ancient past is stored in fossil fuels such as coal and petroleum, and fossil fuels are rich in the elements of carbon and hydrogen, and these sources of energy take very long period of time to form, and once depleted are essentially non-renewable. So, these are non-renewable that naturally occurring sources from which we can get this energy. Now, we have to know that the different forms of energy, and also what are the energy conservation law. So, energy conservation law, it is sometimes called this first law of thermodynamics. In this case, this law says that you cannot create or destroy the energy, only you can change this energy from one form to the energy into another form. Like you can say that a car engine that burns gasoline, that will convert the chemical energy in gasoline into mechanical energy. And solar cells the change radiant energy into that electrical energy, and also heat and light energy can be converted into mechanical energy, chemical energy and electrical energy and back again. So, energy changes its form, but the total amount of energy in the universe remains the same. So, this is called that energy conservation law, and this law is sometimes regarded as the first law of thermodynamics. Now, what are the different forms of energy? There may be some kinetic energy, that may be potential energy, thermal energy, electrical energy, magnetic energy, work as an also energy, chemical energy. Even you can say that some other different types of energy you can have, like nuclear energy, fission energy, fusion energy, all those different types of energy. Now, kinetic energy is basically the energy of motion. Whenever fluid element will change its velocity from one quantity to another quantity, you will see that the motion of this fluid at its different flow rate will have some energy. So, this is called kinetic energy, and potential energy is basically due to the position of the system in a potential field. Whenever any object change its position vertically or you can say at an inclined to another position, you will see there will be a change of potential energy. And you will see that this potential energy may be of different types, like gravitational energy, due to the gravitation and also due to some that chemical bonding of the atoms, and also some other forms, like if suppose a spring when it's change its location, there will be that potential energy will be released there. So, that is why you can say that potential energy is basically due to the position of the system in a potential field. And thermal energy, it refers to several distinct thermodynamic quantities, such as the internal energy of a system, heat or sensible heat you can say, which are defined as a types of that energy transfer. Other forms like electrical energy, magnetic energy, work which are done by machine, work done on system like this. Chemical energy, this is basically a potential energy of chemical bonds. The energy that is stored in chemical bonds is thus considered a form of potential energy. Electrical energy is the movement of electrical charges, charges moving through a wire, that is called electricity, and lightning is another example of electrical energy you can say. Sound is also regarded as an energy, basically the movement of energy it through substance in longitudinal based on compression or rarefaction waves, and this sound energy is produced when a force causes an object or substance to vibrate. The energy is transferred from the substance in a wave. And radiant energy, it is basically you can say that electromagnetic energy that travels in transverse waves, and this radiant energy includes some visible lights, X-ray, gamma rays, and you can say radio waves. And light is one of the type of radiant energy, and solar energy is an example of radiant energy you can say. Sometimes you will see that some energy will be that stored as a mechanical energy, that is called elastic energy, and this is stored in objects by application of a force. Compressed springs there, and stressing its and also stressing of rubber bands are some examples of stored mechanical energy. Nuclear energy, this is also one type of energy which is being stored in the nucleus of an atom. In this case, the energy that holds the nucleus together, and the energy can be released when the nuclei are combined or split apart, and nuclear power in a process that will be called as fission process. You will see that the sun that combines the nuclei of hydrogen atoms in a process which is called fusion. So, fusion is the process where two light nuclei that combines together, releasing vast amount of energy. And fission, this is a splitting of a heavy unstable nucleus into two lighter nuclei by releasing its energy. So, that is why fission is one process by which you can have some energy just by splitting of a heavy unstable nucleus into two lighter nuclei. Whereas fusion is the process for the releasing of energy by that combining two lighter nuclei together into a combination to release this vast amount of energy. And heat energy is the result of that movement of tiny particles, that is called atoms, molecules or ions in the solids, liquids and gases, and heat energy can be transferred from one object to another. The transfer or flow due to the difference in transfer between the two objects. And you will see that due to the molecular or atomic or some subatomic motions, and also that interactions among the molecules, you will see that there will be energy released, and this energy released will be called as internal energy. And this internal energy you can produce by supplying some extra work on this. So, that will be called as work energy, and that work is actually regarded as energy that flows in a response to any driving force there, like applied force, torque, other than temperature, you can say. And it is defined as the positive if it flows from the system, that is work done by the system. In chemical processes, work may for instance come from pumps, compressors, moving pistons and other moving turbines. So, in that way you can get this work for chemical processes just by pumps, compressors, moving pistons and moving turbines, and also you can get this type of work based on that applied force as a torque or some pistons, or you can see elastic forces there. And these work energy will be utilized for transferring of fluid from one position to the another position, or you can use this work energy to change the internal energy or enthalpy of the systems to that particular process where you can get that useful products by its processing. And so, we can say that whatever heat or work, that only refers to the energy that is being transferred to or from the system, and based on which that that process will be assessed, and you can say that performance of the process will be analyzed. And if there is no motion along the system boundary for a particular process, that you can say that that work done will be null or negligible there. So, basically two things are here, heat and work, that will be supplied or it will be that released from the system, and based on which you can say that what will be the process out and what are the efficiency of the process that you can assess based on this. And because this supplying of work to the system or by the system, or you can say that supplying of heat to the system or releasing from the system, you will see that there will be change of internal energy, kinetic energy and also potential energy, and based on which case to case that different chemical engineering processes to be assessed based on the based on each process unit, how it is being used based on this energy supplied. Now, we know that how that energy can be transferred to utilize it for getting that useful products. That energy, whatever heat or work can be transferred by flow of heat, by transport of mass or by performance of work. In this case, you have to remember what are the units generally being used for this energy, and also the rate of energy which is called power. What should be the units, that also to be required to know, because different systems are they are to be used or to be that assessed based on this system of units, and based on which you will see that quantity of the heat in different systems will be different. So, in this case generally the unit for energy is actually denoted by joule, and it is basically that Newton meter. So, 1 joule is equal to 1 Newton meter, or you can say that 1 kg of mass of any object whenever it will be accelerated at a certain value like kg per meter is sorry meter per second square, then you can say that there will be 1 joule of energy is produced or work done will be produced there. So, we can regard it this joule as a unit of you can say that energy, and in British thermal unit its unit will be that BTU, and this that what will be the conversion factor for this joule to that British thermal unit, and also to the calorie, also another important unit by which you can assess this or quantify this that is energy. So, there will be joule, calorie, even British thermal unit. So, here in this slides this conversion of this energy from one system to another system is given. Also the units for power also given in these slides. It is generally regarded as that horsepower or kilowatt. So, 1 horsepower is basically 0.74570 kilowatt, and also 1 kilowatt means 1000 joule per second. That means the how much energy is released or work done per unit time, that will be called as power. So, here the slides the unit for power at different systems is given. Let us talk about the different forms of energy and how it can be calculated. Now, we actually describe regarding that different forms of energy like kinetic energy, potential energy, internal energy, heat energy, electrical energy, all those. So, what is that kinetic energy? This is basically associated with an object's motion, and it is the energy that is carried by a moving system because of its velocity, and the kinetic energy of a moving object of mass m travelling with a speed suppose v can be defined as like half of mv square, If it is regarded as a rate, then we can say that it will be that rate of kinetic energy, then it will be defined as rate of kinetic energy is equal to half into m dot into v square. Here m dot is mass flow rate and v is the velocity. So, half into m dot into v square it will be called as kinetic energy, and its unit will be that joule per second. So, simply it will come as that watt, because watt is a power unit, whereas joule per second it will be the energy per unit time. So, it is regarded as watt. Now, let us do an example for this. Suppose water flows from a large tank into a process unit through a 0.02 meter inside diameter pipe at a rate of 2 meter cube per hour. Calculate the change in kinetic energy for this stream in joules per second. So, in this case you will see that it is given that what will be the volumetric flow rate here. This volumetric flow rate, at this flow rate you will see that water is flowing through the pipe, whereas inner diameter of the pipe is given to you, that is 0.02. So, what will be the velocity of the fluid that is flowing through this pipe? First of all you have to calculate. Since volumetric flow rate is given to you, you can get this velocity just by dividing this volumetric flow rate by its cross sectional area. You have to calculate first cross sectional area, since its diameter is given. So, what should be the cross sectional area? Simply volumetric flow rate divided by cross sectional area, it will be simply that pi d square by 4 if d is the diameter, and if you know that cross sectional area, then you can easily calculate what will be the velocity, simply volumetric flow rate by cross sectional area. So, here you can get this velocity. Now, this velocity will be that through the pipe from its initial condition. Initially that fluid was at rest. So, initial velocity of that fluid will be as that 0. So, you can say initial velocity u1 will be equals to 0 or v1 will be equals to 0, and the final velocity as that u2, that will be equal to just simply q by cross sectional area. So, you can get it, and you can say after that you can calculate what should be the the kinetic energy. So, kinetic energy, that will be half into m dot into v2 square minus v1 square. So, v2 is known to you as per this problem, u2 is 0 here, u1 is 0 here, but again you have to calculate what will be the mass flow rate, since you have given only that volumetric flow rate of the fluid. So, you can get the mass flow rate just that multiplying this volumetric flow rate with its density, then you can get the mass flow rate. Since here the fluid is water, so density of the water is 1000. So, we can say that the mass flow rate will be equal to this 2 into 1000. So, it will be coming as that 2000 kg per hour here. So, if you substitute here this mass flow rate, you can get this kinetic energy finally after substitution, then you can get this kinetic energy as here 0.88 joule per second. So, from hour to second you have to then multiply that this kinetic energy they are second to hour or hour to second, that you have to conversion factor of 3600 you have to use there. So, finally, here in the slides it is given the details calculation of this V2, and also mass flow rate also it is given here as it is 0.56, and then finally this kinetic energy is like this. Let us do another example here. Suppose a liquid is pumped from a storage tank through a tube of 2.5 centimeter inner diameter at the rate of 0.005 meter cube per second. What is the specific kinetic energy of the water? Here density of the liquid as water, you can say it is given 1000 kg per meter cube. In this case you have to find out what should be the specific kinetic energy. Now this specific kinetic energy, basically the kinetic energy per unit mass you can calculate here. First of all you have to calculate it its kinetic energy based on its velocity change. So to calculate that, first of all you have to calculate what is the mass flow rate of that water. This is basically volumetric flow rate into density, then it will be coming as here 5 kg per second, and then calculate the cross sectional area of the pipe. It will be pi d square by 4. Here d is given to you, then after calculation you will get this cross sectional area of 0.00491 meter square, and then velocity of the liquid you can get it volumetric flow rate divided by cross sectional area. Then after substitution of those values you can get this velocity as 4.07. So kinetic energy rate will be equal to half mv square. So after substitution of this value of this mass flow rate, even that velocity there, and finally you can get this kinetic energy rate as 41.41 joule per second. Now kinetic energy per unit mass, that will be regarded as that specific kinetic energy. So that can be calculated just by dividing this kinetic energy by its mass flow rate, then it will be coming as 8.28 joule per kg here. Now what is potential energy? The potential energy is energy the system that is possesses because of the body force that exerted on its mass by a gravitational or some other that field, force field you can say, with respect to a reference surface. Now this potential energy for a gravitational field can be calculated by this equation, where P is called potential energy, M is the mass of that object or material you can say, and G is the gravitational acceleration, and Z is the height of that object from its reference surface. And the specific potential energy can be regarded as P hat, that is basically this potential energy per unit mass, then it will be coming as simply G Z. So potential energy change you can calculate what should be the height change based on which you can calculate its change. It is basically m dot g into Z2 minus Z1. Here Z is the distance from the reference surface, and at two locations if it is there, then you can say that Z2 from that reference subject surface and Z1 also from the reference surface, and then subtracting it will give you that change of potential energy based on this equation given in the slide. Now let us do an example here. In this case again, that water is pumped at a rate of 5 kg per second from a point 100 meter below the earth's surface to a point of 100 meter above the ground level. So in this case you have to calculate the rate of change in the potential energy. So simply here m dot is given to you, G is the gravitational acceleration, that is 9.81. Here this that level change like this Z2 to Z1, here in this or Z1 to Z2, this is basically this difference is coming as that here Z1 is minus 100 meter and Z2 is plus 100. So we can say that this difference will be equal to 100 minus of minus 100. So it will be coming as 200 here. So if you multiply this with this mass flow rate and this gravitational acceleration, we can have this rate of change of potential energy as here 9.81 kilowatt. Now, if we compare this potential and kinetic energy and how it is actually changing, just converting this potential energy to the kinetic energy. Now, let us see this these cars of a roller coaster have the greatest potential energy at the top of the first hill here. Now, as they start their descent, the cars lose potential energy and they gain their kinetic energy, the energy of motion there. Here see in this video on the slides. Here throughout the ride, each time the you can say that these cars or train loss height, it gains speed as a potential energy and then it is transferred into kinetic energy here, and then is transferred into again kinetic energy just by changing its different height of this hill. Likewise, each time it gains height, it loses speed as kinetic energy is transformed into potential energy there. So, based on which whenever it's change its location, you will see that its potential energy will change, and whenever it's change its this velocity, its kinetic energy will change. So, from that that changing its position by its changing its velocity, how this potential energy and kinetic energy will be changed, and this converting this energy from potential to kinetic or kinetic to potential, that you can easily assess is based on this video, or you can understand this. Now, potential energy is energy that is not in use, that is basically stored and is available to do work, and if an object can fall, it has gravitational potential energy. The chemical energy in you will see that in fossil fuels is considered potential energy until released. Fossil fuels have chemical potential energy from chemical bonds which stored energy taken long ago from the sun, and also you can say that biomass or batteries have also chemical potential energy. Here also the spring energy, it is shown in the slides that how this potential energy is changed whenever that expand this spring at a certain length x there. So, there that potential will be potential energy will be calculated based on this expansion of this spring here. So, it will be simply half of k into x square. Here k is called here some constant that is elastic constant here. So, based on which you can calculate what will be the potential energy. Like here example is given, here a compressed spring is displaced at 0.50 meter by its potential energy change. The spring constant is given 200 Newton per meter. In this case, what should be the potential energy that you have to calculate based on this displacement of the spring. Here k is given here 200 Newton per meter, x is given 0.5 meter, then potential energy will be equal to half of k into x square, that simply half into 200 into 0.5 square, that will come 25 of joule. Okay, so we have discussed here regarding that concepts of energy and how different forms of energy is converting from one form to another form. Now, in this case, before going to that balance of energy in a particular system, you have to know that what is that particular system. In this case, the system generally is an object or a collection of object that an analysis is carried out on it. The system has a definite boundary called the system boundary, which is chosen and specified at the beginning of the analysis. Once a system is defined through the choice of a system boundary, everything external to it will be called as the surroundings, and all energy and material that are transferred out of the system enter the surroundings and vice versa, and based on which you have to analyze that system energy which is coming out, which is coming in, and also what are the change of internal energy, enthalpy, potential energy, kinetic energy inside the system. There are different type of system. You will see that some systems will be isolated, Some systems will be closed, some systems will be open, some systems will be adiabatic, some systems will be isothermal. Isolated since they are that does not exchange heat, work or material with the surroundings, and closed system they are in which heat and work are exchanged across its boundary, but material will not be. Open system will be defined as the system where you know that heat, work and materials will be exchanged to the surroundings. And adiabatic systems in that case no significant heat exchange with the surroundings will be happened, and such systems is said to be sometimes adiabatic, and whenever the systems will be operated at an constant temperature, and also that there will be a certain time, and for a particular spatial coordinates, then you will see that heat crosses the boundary will not happen. So, in that case it will be regarded as isothermal system. So, here one system here it is given, this is the closed system, and here red dotted line is regarded as a boundary, and outside this boundary it will be called as surroundings. Now, through this closed systems maybe heat will be in and out there. Similarly, work can be done on the system, and work will be done by the system also. So, energy can cross this boundary of a closed system in the form of heat and work, and the energy balance of the system will be used to determine the amount of energy that flows into or out of each process unit. So, these systems can be regarded as one process unit also, and the balance which will be that used to calculate the net energy requirement for the process, and then it will be assessed as ways of reducing energy requirements in the systems. Then after knowing that system or defining that system boundary, you have to do that balance, energy balance. Now, to do that energy balance, you have to know that basic energy balance equation. Now, as per this that conservation of this energy, we can formulate this energy balance equation as like if it is unsteady, that heat is gaining and it is losing, and also you can say that there will be accumulation of some heat energy. So, if there is unsteady state operation, so based on which we can say that there will be some accumulation, there will be some input of energy, there will be some output of energy. So, based on this concept of this energy equation, we can say that there will be some accumulation of energy based on what will be the energy in the final system, and what will be the energy that in the initial system, and also what will be the net energy that is transferred to the system to change this final system energy from its initial system energy. So, we can then represent it as this accumulation as final system energy minus initial system energy, and it will be then equals to that input minus output like this, and that what will be the net energy here, input minus output, that is transferred to the system, like maybe that some heat energy or that work done by the system, or work heat energy to be supplied to the systems there. So, based on which there will be change of that system energy, it may be gaining its final system energy from its initial system energy there. Now, initial system energy can be regarded as that a summation of internal energy, kinetic energy and potential energy. Final system energy will be regarded as that you again that internal energy of that final state or final condition, kinetic energy and potential energy, and net energy transferred, that will be Q minus W. So, if you substitute these quantities here in this energy balance equation, we can write this energy balance equation here. We can say that net change of energy in the system as an output, or you can say that that will be changed by that supplying of energy or losing its energy from the system here. So, based on this net input to the system, that may change this that system energy from its initial to its final stage. So, based on this we can then formulate this energy balance equation. So, here U f minus U I generally it is that internal energy change from its initial to final, and kinetic energy as K E, this kinetic energy, this is F for final, and kinetic energy, that is I for initial. So, this kinetic energy will be changing from initial to the final. Similarly, potential energy also may be changed from initial to the final. So, what will be the total change of this summation of internal energy change, kinetic energy change, potential energy change, all those will be coming based on that net energy supplied to this system. So, we have here describe this energy balance based on this system boundary, and also how that energy will be done. More details of this energy balance will be described in the next lectures there. So, in the next lecture we will describe this more details of this energy balance, and also other conditions of this energy balance equation, and based on which we will do some calculations based on this energy balance. So, thank you for giving attention for this lecture.